Hello and welcome back. Firstly, a big shout out to Brian for his write-up of PlasMa on the Hackaday website. Now, requests have been coming in for more build details and blank PCBs, printed circuit boards, so I put together a build package available by email request, which includes the schematics, the panel drawings, the bill of materials or parts lists, and test firmware. There's also a build guide document which you can download direct from the Philisound website, and the guide is the definitive document to follow. This video just covers a few topics from the guide to give you an idea of the work involved. Now, it may look daunting at first, although it's just a drop in the ocean compared to a real all-hardware computer, but the design is modular, so you can build and test one board at a time and gradually assemble the full set. It also means there's some flexibility with the final result. For example, you could build a much simpler machine for just the toy emulations with no peripherals. A few of the boards have been retracked since the prototype build to remove workarounds, so I can use these as examples to show some of the assembly and testing. I'll also cover the new memory board, which increases main store from 2K to 64K words. Now, before you start building, set up an anti-static workspace so you don't damage anything. For example, an earthed anti-static mat and a wrist strap. The mat is conductive, so isolate any boards from it before applying power. The board header pins are still vulnerable to accidental shorts, so after each board is assembled, fix them to the bottom panel or a temporary substitute using nylon spacers. In my setup, I placed the panel next to the mat and connected an earth lead between the two. Now, I know a few of you are unfamiliar with MCUs or microcontroller units, so I'll start from scratch, as you'll need to be able to program or flash it yourself in order to run the tests. The MCU module is a Mega 2560 Pro and looks like this. But before doing anything at all to it, we need to verify it works, and the easiest way is to try flashing a simple test program. The firmware folder in the build package contains all the test files you need, including a driver and a flashing utility copied from my Windows 7 PC. If your computer is significantly different, you may need to search the internet for more compatible versions. Now, this MCU module uses a CH340 interface chip to talk to the computer via USB, so the first thing to check is whether your computer can detect this. You'll need a USB cable which connects to your computer, in this example a Type A plug, and a micro USB plug at the other end for the module. And make sure the module is not touching the mat. Plug in the USB cable and the power light should turn on. Now see if that interface chip appears in the computer's device list. Now, how you display this list depends on your computer. On Windows 11, click Start, then type Device Manager and click it when it appears. Now, on this Windows 7 system, click Start, Settings, Control Panel and Device Manager. You're looking for a ports entry like this, but you'll only see the entry when the module is connected and powered. If you don't see it, and the module is definitely plugged in, you'll need to install a CH340 driver. Now, this is also included in the package under this folder. To install it, first unplug the USB cable, then run Setup and wait a few seconds for confirmation. If it installed OK, plug the cable back in and you should now see the entry in the device list. You may need to refresh the screen, although mine appeared automatically after a few seconds. The thing to note is the COM number, as you'll need this later. Now, in my case it's 4, or 4 if you're old enough to remember an old radio classic, but yours may be different. Right, now we'll flash the test program. And the nice thing about these modules is that they have a built-in user-controlled LED, so you can verify things with nothing more than a USB cable connected. There are 2 test programs in the package which do exactly this, called Blink Slow and Blink Fast. And the underlying flash utility is the standard AVR downloader-uploader called AVR Dude, or Dude, I'm not sure. You run it from the command line, but it can be quite daunting as it needs a lot of parameters. So I've wrapped it inside a simpler batch utility called Flash, which just needs 2 parameters. the COM number from before, and the name of the file you want to flash. So, open a command prompt. On my system, it's in Start Accessories. Then change directory or navigate to the firmware folder and enter the following: flash 4 blink slow, and press enter. Now the display shows a lot of information, but basically it writes the file to the MCU, then reads it back to verify. If all goes well, the module's LED will start flashing every second. Now I've included 2 blink programs, so if you ever need to retest the process, you have something different to flash. And the reason being that it's very easy to get confused if the flash fails and you don't notice. The MCU will continue running the existing firmware. Now if you cannot get the flash process to work, you may have been unlucky and your module came without a pre-installed bootloader. Now this is fixable, but outside the scope of this video, so contact me for more information. The bottom line is to check first with the module vendor that a bootloader is pre-installed. You can now solder the header pins to the module in preparation for plugging into the pack board later. When soldering is finished, connect the USB cable again to power up the MCU and confirm the light is still blinking. We can switch off and put this to one side for now and start building the Connectus board. This contains sockets for power and flashing, header connectors for power distribution, and optional components for MIDI and the PS2 QWERTY keyboard. Now this retract board is a simpler version than before. It turned out the machine runs perfectly fine from a 1 amp 5 volt USB supply, so I've removed the 9 volt power option. The USB power socket has been replaced with a more robust Type B socket. And finally, the USB-A socket for programming the OCP has been removed, as the whole OCP idea has been abandoned. I'm sure I don't need to mention this, but make sure all headers and sockets are mounted vertically and flush with the board. A well-known trick for components with multiple pins is to just solder one pin first, then align the component by hand while dabbing the iron on the joint if necessary. If there are a lot of pins, like these long header strips, do the same with a pin at the opposite end. You only solder the remaining pins when you're absolutely sure it's right. Okay, connect a USB power supply to the Type B socket, switch on and confirm 5 volts is on the header pairs, and double check the polarity. If this is all okay, we can move on to the pack board, the peripheral access controller, which mainly just fans out the MCU module pins to more convenient groups of header pins. The only extras are 2 chips for buffering the printer signals, so use sockets here to allow easy replacement. Most boards have a power polarity check light, so solder this first, along with its current limiting resistor and power input header. Connect a power cable pair from the Connectus board and confirm the LED lights up before proceeding. Okay, power off and disconnect, then solder the remaining headers and sockets. Do one final check that there are no power shorts, then power off again and plug in the buffer chips and MCU module. But fit the board standoffs first, as the module covers 2 of the mounting holes. Reconnect the power cable and check the MCU light is still blinking. Now for the fiddly part. The downside of the built-in LED is that it can cause problems in certain situations. And you guessed it, this is one of those situations. The LED clashes with the keypad operation, so it needs physically removing from the module, otherwise the keypad won't work properly. You just need some fine tweezers and good eyesight and a steady hand. And confirm there are no other cables connected to the pack, and then dab the iron on both sides of the LED, and it should just lift off cleanly. There are 4 LEDs in a row, so just make sure you pick the right one. Now I then made a test LED to act as a temporary replacement. You can plug this across the keypad header marked C3 and ground, apply power, and this should flash instead. Now the micro USB socket now needs to be extended to the programming socket on the Connectus board. So make a 3-way twisted cable with a micro plug at one end and a 3-pin female header at the other. Only 3 pins are connected, the 2 data signals and ground. The 5V pin must not be extended. From now on, power must only come from the power socket and not from the programming socket. Right, we're now ready for the final test on this board. The computer cable with the micro USB plug is no longer needed. Instead, you'll need one with a Type A plug, like this. Right, if you haven't done so already, connect this cable from your computer to the Type A programming socket on the Connectus board. Connect the extender cable and power cable from the Connectus board to the pack board. Then connect a 5V USB supply to the Type B socket. Switch on the 5V supply and confirm the light is still blinking. Right, we can now flash the Blink Fast program. So enter flash 4 blink fast, and the MCU light should now blink a lot faster. We've now confirmed the flashing process still works and that we haven't damaged the MCU. You can remove the test LED and flash the Build Test Lights program, ready for testing subsequent boards. So we enter flash 4 build test lights. Right, power off. The cables can be left connected as there is no more soldering on the pack. Right, the next board is the Opper, the operator's console screen. The prototype used an LCD module which happened to contain an SD card socket, but PlasMa has no use for this as it cannot be accessed easily, so you can use modules without this if that gives you more choice. The board was tracked for an SD card level converter module, but this can be left out as it won't be used. When it's all assembled, connect power and data. You can leave out the end 4 wires as these were for the SD card. Power up and the screen should cycle through ASCII characters line by line. And power off. Okay, next up is the timer clock board. Now, this one was not retracked, so I can only show the one from the prototype. Now, I didn't use a socket for the LED driver chip, but it might be an idea to use one if there is enough room vertically. As before, solder the power light first and confirm it lights up before proceeding. Now, the spacing of the LED segments from the board depends on how much you want the display to protrude through the top panel. The details and measurements are in the build document. When assembled, connect power and data, power up and the display should count up rapidly. And power off. Next up are the LED boards, starting with the status board, which is the simplest. You can use different colours for the LEDs, but make sure you read the build document for the ramifications. Use a jig or equivalent to align the LEDs. I use the front panel itself as shown in the construction section on the website, but you may have other ways of doing it. When assembled, connect power and data, power up and the LEDs should cycle through a test pattern, and power off. Now repeat all this for the reg boards and the MagTape deck boards. Now the 2 MagTape boards are powered separately, but the control signals are chained together. And there's a special MT chain test program which confirms these are chained the correct way round. It should light up MT0 first, the left-hand one, then MT1, then both together. And similarly with the reg boards, the reg chain test confirms they are wired in the correct order. Here's the new retracked SD cards board. The card modules are now mounted upside down. This is different to the prototype, but they are much more secure. The test program writes and reads any cards which are inserted and displays the results on the Opper, so this needs connecting as well. The switchboards are similar to the reg boards. You build and test each one separately. The switch states are displayed on the Opper, and when they're all tested OK, they can be mounted onto the top panel and chained together. This shot from the prototype shows each board linked to its left and right neighbour, with longer cables to link rows above and below. So this is effectively one long shift register, so only one set of cables needs connecting to the pack board. The detailed keypad assembly isn't shown here, but this is the simple test program. This is the PS2 QWERTY keyboard test. This is the new RAM extension board. It's the same size as the prototype OCP board and fits in its place. The OCP development idea has been abandoned, so the Mega MCU will continue to do all the work itself. There is a performance hit with this RAM as it's accessed serially, but it allows more interesting program development options, for me at least, and avoids having to continually page programs to and from backing store. Well, this is interesting at first, but gets tedious after a while. Now, the board is mounted next to the pack board, and jumpers connect power and data from it. The test firmware displays the results on the upper. Okay, that's enough for now. There are a lot more details and measurements in the build document, and when everything is finished, download the latest firmware from the website, flash it in exactly the same way as the tests, and PlasMa is good to go. So if you decide to build one, good luck and keep in touch.